Welcome back. Congratulations. We made it to the last session of the day, so thank you. And we were just remarking backstage that there have been so many fantastic questions asked today, and we know that we didn't get to them all. And I could just see them going up in the queue and go, oh, we don't have time. So we're going to see if we can follow up after today and see if those questions can be answered in some way. So look for your email for that. Okay. So we are now on Slido, we're at Caltech 6 is the event code, and it is for Electrified synthesis of molecules. It's our chance to learn how Caltech is leading the development of renewable energy. Dr. Karthik Manthiram is professor of chemistry and biochemistry and a William H. Hertz scholar. He earned his PhD in 2015 from UC Berkeley. He leads here the Manthiram Lab, which studies the development of heterogeneous electrocatalysts for the synthesis and functionalization of organic molecules using carbon dioxide, nitrogen, water, and renewable electricity. Karthik's research has been recognized with numerous awards, including the National Science Foundation's Career Award, DOE Early Career Award, Sloan Research Fellowship, 3M Non-Tenured Faculty Award, American Institute of Chemical Engineers 35 under 35, so many more. So what are the new technologies that advance renewable power? Karthik Manthiram is going to tell us right now for our next session. Welcome. Last session of the day. Welcome.
Awesome. Thank you. All right. Well, thank you all for coming out. I'll be telling you all today about what it'll take to electrify the synthesis of molecules. And our motivation here really is that if we were to achieve this electrification of chemical synthesis, that it could help drive the decarbonization of the manufacturing of the physical world. So if we look out there on Caltech's campus, you look, for instance, at this artificial turf field, there's a huge carbon footprint that goes into manufacturing the fibers that are part of that artificial turf. Even for the seat that you're sitting in right now, there is a carbon footprint behind its manufacturing. Literally every material, the plastics, the fibers, the fertilizers used to grow your foods, they all have a carbon footprint behind them. And we're going to talk today about how we might conceivably drive the decarbonization of that physical world. So we can look at this problem quantitatively. This plot shows the carbon footprint of the top 18 commodity chemicals as a function of their production volume. And you'll see immediately that there is one chemical, ammonia, which has such a large carbon footprint that it actually has its own y-axis. That if we were to have plotted everything on the same y-axis, ammonia would be up top and everything else would be compressed down at the bottom. So it is essential that if we are serious about driving the decarbonization of chemical manufacturing, that we have to do something about ammonia. But on top of that, if we do want to achieve deep decarbonization of chemical manufacturing, then we will also have to do something about all these other chemicals shown here, things like ethylene, propylene, methanol, BTX, and ethylene oxide. So if we want to drive this decarbonization of chemical manufacturing, then we should start by putting out a paradigm that could guide our journey through this decarbonization. And so I show three conventional paradigms for chemical synthesis here. First, on the far left-hand side, we have biosynthesis. This is how nature synthesizes a particular molecule. So if we were to apply this definition, for instance, to ammonia, that would be a nitrogenase, an enzyme which can take nitrogen, water, with the power of ATP to be able to make ammonia. On the far right-hand side, we have total synthesis. This is the desire to make a molecule beginning with anything that is simple and commercially available. And so if we were to stretch this definition a bit for a molecule that is as simple as ammonia, that would mean the Haber-Bosch process. That's how we make ammonia today. We start with methane and water and nitrogen, and we commercially combine those to be able to make ammonia. What we're working on in my group is a way of being able to make this physical world, to make these chemicals beginning with just 3 molecules. So rather than using anything which is commercially available, we're using just CO2, nitrogen, and water. So these are 3 molecules which give us a source of 4 atoms that we can now stitch together to be able to make the physical world. And we drive these reactions using renewable electrons, that if we use the power of the sun or wind to be able to drive these bond breaking and bond forming steps, that we can do chemical synthesis more sustainably than if it were driven by temperature and pressure. These are the conventional variables or driving forces that are used in chemical synthesis. So we can look at how we would implement this. We're starting with nitrogen, reducing it, fixing it to be able to make ammonia, taking CO2, converting it to be able to make CO and ethylene, and then starting to combine these first reduction products with additional chemistries like oxygen atom transfer to be able to make products like ethylene glycol, ethylene oxide, to make lactones and even amino acids. So these are a few examples of the types of products that we're aspiring to make, beginning with very simple and ubiquitous precursors. So we'll look at two examples today. The first will be the desire to make ammonia beginning with nitrogen, to do that at room temperature and ambient pressure, conditions that are very different from how we make ammonia today. And then we'll look at this desire to convert olefins and water into epoxides, that if we were to do this, we could make epoxide synthesis much more sustainable than it is today. So we'll focus in first on making ammonia. So we can take inventory of the challenges that ammonia synthesis faces today. On this plot here, we have dollars per ton of urea. Urea is an ammonia-containing fertilizer. And we have several countries here in sub-Saharan Africa, Burkina Faso, Cote d'Ivoire, Ghana, Mali, Nigeria, and Senegal, and their price for urea as compared to the international average. And one thing you'll see immediately here is that the price of fertilizers in these countries is 2 to 3 times the international average. Now, those fertilizers all cost about the same up until they're brought to port. It really doesn't matter where that vessel is going in the world through the oceans. But it's that journey from port to where those fertilizers are ultimately used that can vary so much in cost depending on where you are in the world. And in these countries in sub-Saharan Africa, Burkina Faso, Cote d'Ivoire, and others, these are countries in which the money needed to make investments in infrastructure, to make fertilizer distribution cheap, doesn't exist. And this has been a long-standing challenge. So these resources have not materialized for the necessary investments. That in turn means that fertilizer prices, of course, are higher. There's lower fertilizer usage, poor crop yields, and that in turn is one of the factors that contributes to severe malnutrition in sub-Saharan Africa. So this is an important problem to solve. We can look at how we make ammonia today and think about why that contributes to the problem that I'm describing here. We start today with methane and water. We combine those to make hydrogen. So we're ripping hydrogens off of the carbons and off of the water. As a result, the carbons and oxygens combine to make CO2. So we have a stoichiometric CO2 footprint that comes out of this reaction. This is done at greater than 700 degrees centigrade. We then take that hydrogen, we combine with nitrogen to make ammonia, and we do this at 400 to 500 degrees centigrade and 150 to 250 bar of pressure. So you'll see two immediate problems here. The first is that we have an enormous CO2 footprint. And this is so large, of course, that it is part of why ammonia has the largest carbon footprint of any chemical that we manufacture today. And the second problem is the harshness of conditions, greater than 700 degrees C for this first step, and 150 to 250 bar of pressure in the latter step. And this means that this is chemistry that you can't practice close to where it's needed. You can't do it in a distributed fashion. These conditions are sufficiently harsh that you have to do this at really large scales and in a centralized fashion. And that's why there are a relatively small number of ammonia synthesis plants worldwide from which we distribute that ammonia. And as a result, we have a heavy reliance on infrastructure for distributing ammonia. And so if we were to dream about the characteristics that we would desire for a next generation method of making ammonia, we would first want it to eliminate the CO2 footprint. And second, we would want it to operate at more benign conditions, at room temperature and ambient pressure, that if we were to achieve that, that ammonia could now be made closer to where it's needed, that we would no longer need to distribute it over long distances, which contribute in some parts of the world to higher costs for that fertilizer. And that's really the goal that we have in the work that my group is doing on ammonia synthesis. I want to share a second source of motivation, and this is really something that's emerged in just the last few years. I'm sure we're all familiar with the hydrogen economy, the desire to be able to power certain parts of the world and our daily activities with hydrogen as a molecule for energy storage, and to also use clean hydrogen in chemical manufacturing. So the problem with this paradigm to use hydrogen as a method of conveying energy is that hydrogen doesn't really have a very high energy density. So if we start, for instance, with water and we split it and we make hydrogen, moving that hydrogen around to where it's ultimately needed is really expensive. And we can see that here in this table, that the energy density of hydrogen at 1 bar is just 0.03 kilowatt hours per liter, which is really low. We can pressurize it going up to 700 bar, which is, again, a really high pressure. And if we do that, the energy density of that hydrogen increases to above 1 kilowatt hour per liter. But that, again, is a really high pressure. It takes so much energy to compress this hydrogen that you lose about 10 to 20% of the initial energy content that the hydrogen has. So that gives you some idea of just how energy intensive even just that compression is to get to a reasonable energy density. And as a result, this adds about 10 cents per kilowatt hour. And you can reference this to the cost of renewable solar or of wind, typically around 5 cents per kilowatt hour, sometimes even a little less. This storage in hydrogen adds a lot of cost. So if you're trying to take renewable electrons and put that energy into a chemical carrier like hydrogen, techno-economically, this just isn't viable yet. And so what we can look at instead is filling this box with a secondary carrier. We can take that hydrogen that we're making by splitting water, and we can now associate that hydrogen with nitrogen to be able to make ammonia. And this ammonia now we can transport at a much lower cost for reasons that I'll describe in just a moment. We can then dissociate that ammonia close to where it's needed, making hydrogen, releasing nitrogen, which we can just vent into the atmosphere. And this hydrogen then can be used in whatever terminal application was envisioned otherwise. And so here, ammonia becomes our dominant energy carrier. And so we can look at this by the numbers. Ammonia has an energy density of 3 kilowatt hours per liter at just 10 bar. So that, of course, is much higher than hydrogen, which existed at only 700 bars. So we see an immediate advantage there in terms of energy density. And on top of that, the compression losses, the energy needed to get to 10 bar, is just 2 to 3% of the initial energy content of the ammonia. So this is much more usable from a techno-economic perspective. And the cost of transporting and storing that ammonia is just 1 cent per kilowatt hour. So the techno-economics of this start to look better as well. So 2 sources of motivation here then, right? One is fertilizers, which I talked about on the last slide, and the second is energy storage. And this may seem a little distant, but there are many pilot projects that are being announced worldwide. Of any chemical carrier out there, ammonia is getting the largest investment today relative to anything else that's been proposed out there. So this is a big change that's happened in just the last couple of years. But there's still a lot of research to be done to actually enable the viability of ammonia as an energy carrier at scale, and that's exactly what we'll be talking about today. So if you look at how ammonia is made today, you all may remember from 2 slides ago that I mentioned that pressure is important, that you have to reach pressures of 200 to 250 bar to drive this conversion of nitrogen and hydrogen to ammonia. And what we want to look at is if we can replace that pressure with voltage instead, that this could be a much more benign driving force to use to drive this chemical reaction. So we'll focus in on this particular step of this process. This color map here shows conversion, which is a variable x that ranges from 0 to 1. Anywhere the conversion is 0, that means we are entirely at reactants, just nitrogen and hydrogen. And if the conversion goes to 1, that means we have fully gone to ammonia as a product. So based on this color map, we'd want to be in regions that are red as opposed to those that are blue. So here in this color map, we have temperature on the x-axis and pressure on the y-axis. And so looking at this, we may decide to start at the origin, that the thermodynamics at that point look favorable. However, there is a kinetic challenge. Even though this reaction of nitrogen and hydrogen would go to ammonia if given eternity, which is all that thermodynamics is telling us, kinetically, it doesn't work out. And for that reason, we're forced to increase the temperature up to about 500 degrees centigrade. And at that point, these bonds actually become labile. The nitrogen triple bond can be broken over a suitable catalyst, and it can reassociate with hydrogens to make ammonia. The kinetics start to work out. But you can see the problem based on this plot, which tells us just the thermodynamic reality here, which is that we have a very, very small equilibrium conversion. That sure, the bonds are breaking and forming, and that's all happening from a kinetic perspective, but we stop at a less than 1% single pass conversion if we are at 500 degrees centigrade. Now, the way we solve that is by pressurizing. Because this is a reaction in which we have a reduction in the number of moles, pressurizing by Le Chatelier's principle allows us to shift the equilibrium of this reaction to the right. And so if we go up in pressure to 200 to 250 bar, we can now get to an ever so slightly lighter shade of blue here, where we have about a 15% single pass conversion. And this is actually how we make all the world's ammonia today, with a 15% single pass conversion. So it's really a testament to engineering that after a century, we have gotten this process to a place that we can feed the world with fertilizers that are cheap enough, even though the molecules passing through this reactor only have a 15% single pass conversion, which is really, really small. And so we can consider instead to use voltage to recover conversion in the place of pressure. This plot has the exact same x-axis. We still have temperature, but we've now placed voltage on the y-axis. And you'll see a plot that looks really different. We could start, for instance, at 500 degrees centigrade. We could now apply a third of a volt going up, and we would reach a region which is deep red in color, near unit conversion, greater than 99% conversion of nitrogen and hydrogen to ammonia, with just a third of a volt. And I remember doing this calculation about 5 years ago, and what we recognized here is, of course, that this is less than the voltage of a AA battery, right? A AA battery is 1.5 volts. With a third of a volt, you can shift this reaction. You can do far more than you could do with thousands of bar of pressure with just a really tiny voltage. And that really, for us, has been extraordinarily motivating to try to figure out ways of using voltage to drive chemical reactions. This at its very core is why we want to electrify chemical synthesis, because there are things you can do with voltage that temperature and pressure could really just never do. Now, it turns out that voltage helps not just the thermodynamics, it helps the kinetics as well. So you can, in fact, come back down in temperature, even down to room temperature, and drive this reaction with voltage alone to help the thermodynamics and the kinetics of this process. So you may look at this and think, well, should we electrify every chemical reaction? If this looks good for ammonia, should every chemical reaction out there be driven with electrons instead of temperature and pressure? And the answer to that, I think, is actually no. There are some reactions, like the one that I'm showing here, to make nitrogen and hydrogen into ammonia, that benefits from electrification. There are other reactions, though, that are better driven with temperature and pressure. And it all comes down to their thermodynamics. We've actually published a paper last year, or in 2021, sorry, so 2 years ago now, that shows how just based on thermodynamics, you can actually determine whether a given chemical reaction should be driven with voltage, temperature, or pressure. And so one can obtain very clear guidance to know a roadmap for the next 20 years as to what our targets should actually be. So what I told you about ammonia on the previous slide, that it benefits from electrification, may give you the impression that this should be possible already. But it turns out that even though the theory of what I'm showing on the previous slide looks promising, that there are still challenges in developing catalysts that have suitable rates for driving this reaction. And what I want to share with you today is a process whereby you can use lithium metal to actually drive this reactivity. And so here, starting with lithium metal, one can react with nitrogen. That lithium metal reacting with nitrogen can spontaneously make lithium nitride. This is one of the really special things about lithium metal, that if you expose it to nitrogen gas, it will spontaneously break the nitrogen triple bond. That even though that triple bond is so strong that in the presence of lithium metal, it dissociates and it makes a solid state form of nitrogen, here Li3N. That lithium nitride can then be protonated by a proton donor that I keep generic for now. That in turn leads to exchange of the lithium ions with protons. That in turn makes ammonia as a product, lithium ions which are discharged into solution, and those lithium ions can then be plated so that we return to lithium metal and can continue around this cycle. So there have actually been a few demonstrations of this. So we can look back about 5 years ago, there was a demonstration that showed how you could take lithium metal that's plated out of a lithium chloride, lithium hydroxide bath operating at 400 to 500 centigrade. You could take that lithium metal, you could cut it up and put it into a beaker, you could introduce nitrogen gas, you could make lithium nitride, you could then introduce water as your proton donor, you'd make ammonia, you could boil off the ammonia in water, you'd leave behind lithium hydroxide, and you could dump that back into the first bath, and you could continue around this cycle. They demonstrated a greater than 80% Faradaic efficiency for making nitrogen into ammonia. And Faradaic efficiency is defined as the fraction of electrons that go toward your desired reaction. So if it's 80%, then 80% of the electrons went towards making nitrogen into ammonia. So this is pretty good from an electron-based selectivity perspective. But we can probably all agree that we're not going to feed the world with a reaction that involves solids, that solids handling is really challenging, and we have macroscopic chunks of lithium metal here, which we really want to avoid, right? We know that there's a safety hazard in having large pieces of lithium metal. So even though this is a good proof of concept, there are a lot of issues with this implementation. What we've been interested in instead is a report from 1994. There was a group in Japan that actually demonstrated this ability to put two wires into a solution, that one of these wires, a copper wire, you could actually plate lithium ions at to make lithium metal. That lithium metal could then react with nitrogen gas that you're bubbling through, making lithium nitride. It could then react with a proton donor, ethanol, to make the lithium nitride into ammonia. And all that could happen in a single beaker. So we were really intrigued by this report, this isolated report that demonstrated that a one-pot reaction could perhaps be done. The issue here was that the Faradaic efficiency was really low. It was just 8%. So a very small number of electrons, just 8% of the electrons were going to the right place. The rest were going towards undesired reactions in this process. And the rate was just 0.55 nanomoles per centimeter squared of electrode area per second, which we can probably all agree is really small. And so this was a pretty humble starting point in terms of electron-based selectivities and rates from where we wanted to try to make improvements. So as we started working on this chemistry, the first thing that we recognized was that we needed to make a more robust reactor architecture. So we went from having two tiny wires dangling in a beaker to something that was more scalable. Here we have a copper foil cathode on the left side and a platinum foil anode on the right side. We have a separator, which just helps to keep the two compartments here apart from each other. We have an electrolyte that is lithium tetrafluoroborate with tetrahydrofuran, still with ethanol as the proton donor. And we, in this cell, are bubbling through nitrogen gas. That nitrogen gas is reacting with lithium metal that's deposited on the surface of the copper cathode. These are really small amounts of lithium in inventory, so the safety hazard is really eliminated. And what we found is that it is this journey of nitrogen from the bubble to the surface of the electrode that's limiting. It's not actually the reaction, this breaking of the nitrogen triple bond that's the hard step. It is the physical movement or transport of nitrogen gas from the bubble to the surface of the electrode that was the step that was limiting the rate of this reaction. And so that's really the problem that we set out to solve at the very beginning. What we drew up on a whiteboard was a reactor that looked like this, that we could start with that we could implement a gas diffusion electrode on both sides of this reactor, that a gas diffusion electrode, which is just a porous medium that facilitates contacting, could allow us to bring together nitrogen gas with a liquid electrolyte with the solid phase here, which is conducting the electrons. So there are three different phases, solid, liquid, and gas, that could all be brought together within this porous medium that we call a gas diffusion electrode. And we reasoned that if this were implemented, then both gas and liquid could meet each other at the solid surface. So we would no longer have this journey of nitrogen gas from bubble to surface of the electrode be limiting, because the gas would have direct contact with the surface of the electrode as shown here. And so we implemented the stainless steel cloth as a means of driving this reaction, so that's what we're using as a gas diffusion electrode. And at the anode, we did the exact same thing. Here we're oxidizing hydrogen, and we're using a platinum catalyst that's deposited on the surface. So this was our first step towards trying to solve this transport limitation within this reactor. And what we found was that what would otherwise be a transport limited rate of less than 10 nanomoles per centimeter squared per second, or even less than 1 nanomole per centimeter squared per second, as shown in the previous report by Sunetto et al. From Japan, we can now reach 30 nanomoles per centimeter squared per second. So we can see immediately that we've actually alleviated this transport limitation. We can now drive much faster rates of interfacial reaction just by implementing this very simple method of contacting gas and liquid at the surface of the electrode. The second benefit of this is not just that the rates are higher, it's that the Faradaic efficiencies are now also much larger. So what was just 8% before for this one-pot realization, just by solving this transport problem, by getting the nitrogen to where it needs to go in the reactor, we can now get nearly half the electrons to go to the right place. We have a Faradaic efficiency of nearly 50% now by implementing the gas diffusion electrode. So there were many fundamental puzzles in this chemistry. We see here this ability to practically improve rates of reaction, but we were stumped in our lab as to why certain electrolyte compositions work well, while others don't. The essential question to us was, why does ethanol work well? Why does tetrahydrofuran work well as a solvent? Why not use a different solvent like DMSO, or why not use an ether, a different type of ether as a solvent? And so this for us was extremely hard to answer. We tried hundreds of experiments, trying different solvents and different proton donors, and putting up here a sampling of data showing the Faradaic efficiency for different proton donors in this chemistry. And honestly, we really just couldn't make sense of this. This looked about as random as could be. We continued to make hypotheses. We would do 10 more experiments. We'd look at the data again. We'd come up with a better hypothesis, and we would try again. And we continue to march through, finding no success whatsoever in explaining why certain proton donors and certain solvents worked well for this chemistry. The final hypothesis that we made in this space that yielded a robust result was that it had to be what is called the solid electrolyte interface. That lithium metal is so reactive that if you take lithium metal and expose it to any type of organic solvent, that you will instantly decompose that organic solvent on its surface. You will reductively break it down and make a thin layer on the surface of the lithium metal. And this thin layer is what we call the SEI, the solid electrolyte interface, that the lithium is a solid, that we have a liquid electrolyte out here, and its decomposition generates what is called the solid electrolyte interface, that somehow that must be controlling why certain proton donors and certain solvents work well and others do not. But that was just a hypothesis, and there was really no means of proving this until we started a collaboration with a group that developed a technique known as cryogenic electron microscopy. And some of y'all may have heard of this technique. It won the Nobel Prize a handful of years ago in the realm of structural biology, that one could use electrons to image particular configurations of atoms in the context generally of proteins, that if you cool that sample down, which is what the word cryogenic is telling us, that if we cool it down, it will limit the decomposition of that material or that protein that we're looking at. And if we now have a really sensitive electron detector on the other end that can measure single electrons, that we can now image proteins. And that really has driven a revolution in structural biology, that you can use cryogenic electron microscopy to determine the structure of proteins. And what we decided to do here was to bring that tool to material science, to bring that tool to look at even the interface here of lithium metal with an organic electrolyte, that we could actually see the structure of this interface with unprecedented resolution without having the electrons decompose or further break down the surface such that the act of observing the interface wouldn't somehow perturb it. And that really was our goal here. And so we developed an electrochemical cell in which we could run this chemistry, that we could then take that electrode, plunge freeze it in liquid nitrogen, and send it into a cryogenic electron microscope. And we can now actually look and see this interface that we have lithium metal here. We can actually image and see individual atoms. And we can look on the surface here and see a very thin decomposition layer here. So this dark region on the surface is the solid electrolyte interface. And it contains domains of, for instance, of lithium hydroxide and other more amorphous regions from THF breakdown. When the solid electrolyte interface is conformal, as I'm showing here, and rather dense, it actually entirely stops reactivity in the system. The lithium metal can no longer access nitrogen or the proton donor to be able to make ammonia. When instead you can make a fractured solid electrolyte interface of the sort that I'm showing here, which is porous and disorganized, you can now activate lithium metal to be able to drive this conversion of nitrogen to ammonia. And what we found is that if we take electrolytes that work well, that have high Faraday efficiencies, and then we take electrolytes that don't work well, that have low Faraday efficiencies, we could rather easily classify them into these two types of images, ones that are conformal and don't work well, or SEIs that are porous and fractured that allow for transport of nitrogen gas through them such that the reaction can happen. And so we now finally had a physical handle, something that we could see and believe that could tell us as to why a certain solvent or certain proton donor works well and another doesn't. And this was really driven by an interdisciplinary advance, taking a tool from another field and bringing it here to catalysis to be able to understand something new. So I've told you a lot so far about ammonia synthesis, and I want to now spend just a little bit of time here at the end to tell you about the use of water as an oxygen atom source. And I'll spend just a few minutes here to tell you about one more chemistry in which electrification could be helpful as well. So we can look out there and see how we do epoxidation chemistry today. We typically start with an olefin, react with oxygen, make, for instance, ethylene oxide as a product. So this is a very conventional route. If this were the reaction, I would really have no qualms. This is done at just 270 to 290 degrees centigrade and 20 bar of pressure. But the issue is that a lot of this ethylene oxide over-oxidizes. It doesn't stop there as a product. Instead, we continue to oxidize, going all the way to CO2 as a product. And this, in part, is why epoxide production has the 5th largest carbon footprint of any chemical that we manufacture today. It's because of this over-oxidation. So it is really important that we find ways of eliminating this carbon footprint. This has been recognized for some time, so others have tried to develop alternative approaches. I show here, for instance, the chlorohydrin process, by which one can react an olefin with hypochlorous acid, making a chlorohydrin. This chlorohydrin can then be treated with base calcium hydroxide, and you make the epoxide. But you also make a calcium chloride side product. And this calcium chloride side product is sufficiently a problem now because of the brine discharge that you have from those plants, that permitting of the chlorohydrin process is actually decreasing now. So we're seeing fewer and fewer plants getting approved in jurisdictions that recognize the environmental challenge of having this salt discharge stream. One could instead use peroxides. These are relatively popular processes now, starting with an olefin, reacting, for instance, with a peroxide like metachloroperbenzoic acid or hydrogen peroxide. You can make the epoxide as a product, but my friends who are process chemists tell me that these reactions remain relatively dangerous at scale. There continues to be, on average, 1 fatality a year from epoxidation plants. And these are reactions that all too often go wrong because you have organics in contact with really strong and reactive oxidizers. So we can see here that there are a lot of reasons to innovate on epoxidation chemistry. The carbon footprint, the presence of environmental discharges that are unfavorable, and safety, all of which conspire to motivate us to make new methods of driving epoxidation. So what we dreamed of in our group was that it would be really interesting if we could instead do epoxidation with water alone. If you could take an olefin, react with water, make an epoxide, and co-produce hydrogen. That really this is glorified water splitting. That instead of breaking apart water, making hydrogen, and struggling to recombine those oxygen atoms to make O2, and then just venting it to the universe, that we could instead take those oxygen atoms and place them on an olefin to be able to make an epoxide. That was really our goal. And so in this reaction, what we'd want to do is activate water at the anode, take that O atom, place it on the olefin, and then take the electrons, send them through the external circuit, take the protons, send them through the electrolyte, and make hydrogen on the other side. And we reasoned in our early work that manganese oxide could be a good catalyst for this, that it's known to activate water, but isn't so good at recombining those oxygen atoms, and that may give us just enough time to have this olefin sweep in, pick up the O atom, and make the epoxide as the product. So we actually found in our early work that we could reach a 30% Faraday efficiency. We were really excited to see that as a first demonstration of this reaction. We found a 100% Faraday efficiency for making hydrogen on the other side. This was initially with a model substrate cyclooctene, just to demonstrate that this reaction was even possible. We've then continued to develop new generations of catalysts. Here I'm showing that you can decorate the manganese oxide with iridium single atoms. That these iridium single atoms make a local environment on the catalyst that is even more favorable for epoxidation, that we can take what was 30% for a Faraday efficiency on manganese oxide and make that 50% instead with an iridium decorated catalyst. And now in our lab and unpublished results, we've gotten up to 80%. So we're continuing to make this a more and more selective process, one which is actually being noticed now by industry, and we're hoping that we'll be able to actually spin this out in something that could help drive decarbonization of epoxide synthesis. So this isn't just about epoxidation. You could imagine that you could also perhaps use this to drive other types of oxygen atom functionalization. Lactonization is a second chemistry that we've achieved where you can take a cyclic ketone, you can actually insert an O atom into this ring, and in doing so, make a lactone. And lactones are, of course, really interesting as biodegradable monomers. And so this is a more sustainable way to access a monomer which will probably have increasing relevance and interest in the years to come. So the last thing I'll mention is that there are two more parts of our group that I just want to very briefly bring attention to here. Carbon dioxide utilization is really important, and I haven't touched on that particular topic here, but we're working actually on ways of being able to take CO2 and convert it into long-chain hydrocarbons, that you can take a C3 molecule and selectively make it into a C4 by stitching on one more CO2. There's a really interesting chemical toolkit developed there. And we're also working on new ways of enabling efficient electron transfers to bacteria, that if we could achieve this, we could harness all the selective enzymatic machinery to make molecules selectively, but to do it with renewable power, to do it with the power of the sun and the power of wind, to drive bacteria to do efficient chemical synthesis as well. And with that, I'd like to thank the students and postdocs who have been incredible companions on the scientific journey. They've shown such great dedication to the science that they're doing, and many of these concepts have actually come from them. So I'd like to thank them for their dedication to this science, and all of you as well for joining in today. And I know we'll now transition to Q&A, so thank you all.
Thank you, Dr. Mantherum. So we're going to actually begin with a couple technical questions and then lens out to the more global questions. So Kevin, I think, who may be an expert in this field, two questions. Has your lab worked with perhaps more active lithium alloys for ammonia synthesis? And for context, what is the activity for conventional Haber-Bosch catalysts? And the units are listed there, which I can't say. Can you say
Absolutely.
what the, yes, what are those units?
Nanomoles per centimeter squared per second, right? So this will help to give us some idea as to how to actually benchmark these catalysts.
Yes.
So first on the lithium alloys, we've actually tried a series of ways of alloying lithium metal with other alloying agents as a means of trying to modulate its reactivity. And what we found so far is that it is just lithium metal that does this reaction effectively. As soon as you introduce an alloying agent like tin, as one example, or many other elements of the periodic table that like to alloy with lithium, that reactivity of the lithium metal is changed. It no longer makes what we want it to. So in the units question that was just asked, if you look at conventional Haber-Bosch, the reactivity there is around 3 nanomoles per centimeter squared per second. So we're about 10 times higher than that in terms of per area reactivity at this point. So it's really neat to see that these rates are actually higher than what's commercially practiced, although there's still a lot of work to do in terms of further increasing the Faraday efficiencies and increasing the energy efficiency of this process. One of the remarkable things about Haber-Bosch is that after a century of innovation, that reaction now has a 70% energy efficiency. What we published that I've shown here today is at a 3% energy efficiency. In unpublished work, we're now at above 10%, so we're making progress. But this really does need to get above about 25% in our view to be something that's commercially viable. What gives us motivation, though, is that Haber-Bosch, when it was first commercialized, was at around 10 to 20% energy efficiency. So that's a process that took several decades, and already we're starting to see progress to get above 10%. So we do, of course, want to continue to see that increase, though.
If this process is exothermic, could that heat be then used as a different means of energy production as well?
Absolutely, yeah. So the reaction of nitrogen and hydrogen is indeed exothermic. That's part of why when you increase temperature, you disfavor the equilibrium because it's a reaction that generates heat. So if you think back to those color maps, that's something you can justify just based on their appearance. That heat you could actually use, and so with appropriate heat exchangers, you could now couple this to other chemical reactions that could make use of that heat that you're generating. So that kind of integration is really important when one looks at commercial viability of a process.
For this conversation, we could solve it all right now. So two more quick technical questions. What do you hypothesize your results would be if the state was brought into a plasma state instead of a gas? Also, does the carbon you use in this process help reuse carbon waste?
Yeah. So plasma-based reactivity is really fascinating. This is one of the other contenders out there. There are, in fact, startup companies that are trying to use plasmas to activate nitrogen to make ammonia. To me, it's really fascinating because there's a long history to trying to use plasmas and electrical arcs to make nitrogen into ammonia. In fact, before the Haber-Bosch process won out, and this was in the 1920s, there was a flurry of activity in the 1910s to try to use electrical arcs to make nitrogen into ammonia. And there was just a ton of motivation worldwide to make this happen because there were wars being fought over access to natural fertilizers, essentially over bird poop, which was one of the best fertilizers available then. So if you look back, there's this rich history to trying to use electrical arcs and plasmas and other means to activate nitrogen. The challenge always has been energy efficiency. Those processes have really low energy efficiencies. There, of course, could be a breakthrough that makes it possible, but that's exactly where fundamental science needs to be focused to try and make that happen.
Last question about Haber-Bosch, which is really trending right now. And okay, are there techno-economic or climate benefits to direct electrochemical synthesis of ammonia over a Haber-Bosch process, HB, that uses carbon-free H2 synthesis by, e.g., water electrolysis?
Perfect, yeah.
Okay.
And so if we were to do a techno-economic analysis based on what we think is possible in the next couple years, we would likely be making ammonia that's about 2 to 3 times more expensive than Haber-Bosch today. If you think back to one of the earlier plots that I shared, looking at how much fertilizers cost in some parts of the world, you'll see that this process could actually start to be competitive, given that fertilizers, especially in stranded locations, are more expensive. But we do see a decade of research ahead of us to be able to make this something that could better compete with Haber-Bosch. In all likelihood, these will be complementary technologies. There are other ways of decarbonizing Haber-Bosch at immense scales that are likely to be attractive. And what we're developing is likely to be attractive at smaller scales of production, local production of ammonia. So I think this sort of complementary ecosystem of technologies in all likelihood will emerge.
You say 10 years, is completely green energy possible?
So there's a lot of work to be done, and there are a lot of parts of our economy that are difficult to decarbonize. And so there are the simple to decarbonize things, and there are the hard to decarbonize things, right? And today we've talked about a handful of things that many regard to be difficult to decarbonize parts of the economy. There are others like cement and steel production that also have really large carbon footprints that are thought to be difficult to decarbonize. And part of that's technological, but more of it is techno-economic in many ways, right? If we had all the money in the world to decarbonize chemical manufacturing, we could find a way. But we know that the world and the developing world in so many ways relies on these chemicals and materials, that there's a strong connection between quality of life and cheap access to cement and steel and ammonia and so many other things. And so we know that we need cheap solutions to be able to get these things out. And that certainly gives a lot of motivation for the science as well.
And finally, what could alumni, and this is a trick, how could alumni support this work becoming more practical in the market?
Yeah, so I think there's a lot, just an interaction through thought and conversation. We do have quite a few alumni who come through our lab, and it, for us, can be eye-opening to see something from a different perspective. I think sometimes in the depths of a lab, working on a problem, if you're able to see it from someone else's perspective, a lot of good things can happen. And so for those who are interested, I'd love to have you all reach out and come by and chat with us more about this chemistry.
Thank you so much, Dr. Manthiram. That's fantastic. Please give a warm hand.
Thank you all.
Thank you so much. Well, that concludes the presentations today. I want to say thank you so much personally. It's been really fun to be here today. We've pushed our boundaries together as a community, and it has been so fun to engage with you all. The Slido was interesting. Caltech people were uniquely intelligent, uniquely thoughtful, and sometimes actually quite hilarious. So that's fun. And to close, finally, I'd like to bring out Ralph Amos, the head of the CAA, the CEO of the CAA.
Don't leave.
Okay.
Everyone, please join me in thanking Sandra for doing such an awesome job today, right?
Thank you so much.
I mean, really, you bring to life what is Caltech, you embody it, and you glue it together in a way that is of a community, and it's important. So we really appreciate you.
My pleasure.
Thank you.
Okay.
Awesome.
Now I'm going.
Now you're going. Now you can go, right? And thank you for being here. Thank you online. A total of about 800 techers joined in today. Throughout the world and in this room. And we couldn't do this without you. We do this for you, but it really is about building stronger community for a place we think is very important. We want to keep the Alumni Association strong. Our job is to ensure the success and well-being of graduates around the world. And we have 26,000, nearly 26,000 alumni who live there. There's 5,300 who are just in Southern California. So when we get ready to do tables for techers, I hope you will sign up. Raise your hand, open up your home, break some bread with techers. We'll help bring the guests. And you're going to do it?
I'll check with my wife first.
Yes. Very important, sir. You should check with your spouse or other. Just don't start bringing people into the house. This could be bad. We also want to remember that our students, many of them will be out in the world. So you might be able to invite students who are on an internship or they're doing a postdoc at a university. If you're in a small town, but you're in a university town, you're probably going to have a few techers on the faculty or staff there. So we think this is going to work. We plan to have hundreds, if we can, of these dinners going on concurrently over 2 nights. So thank you for being here. Thank you for keeping Caltech strong, keeping them in your heart and your minds. And we'll see you soon. We have the fall coming up, and we have a lot of activities planned. So have a great evening, be safe, and go Tech. Good night.